That's the idea for light units. Are there any questions about how that all proceeds? Yeah?
My question is, why you can't add the 2 tens in the bottom?
Did I cancel? I just crossed them because I wanted to keep track that I wrote them down. I should have crossed these out too because I wrote those out as well. I said 3 times 3.6 is 10. So I just did it so that I didn't multiply them again. I didn't want to.
You just add the exponents.
I added the exponents. I said that's 10 to the 8. Okay.
And
Make sure that I don't
then
do
you rounded up the.
3 times 3.6 was rounded roughly to 10.
Okay. Got it.
When I say that you can do all the homework without a calculator, this is what I mean.
Wait, so
Because you can do
just,
this sort of approximation, you'll get the right answer.
Wait, I have a question. So you always want to do the whole number?
Yeah.
Oh.
Yeah. I typically do that. And the reason that works is because you have about 50% leeway in all of your calculations in this class. Because we're dealing with such enormous scales and such small scales, oftentimes we don't have better estimates than about that accuracy. And so taking an estimate like this is perfectly fine, and in fact is a very good thing to do. Any other questions about this part? We have 2 more things to sort of get through, and then I'm going to sort of wrap it all up. But what I wanted to get through is that there's sort of an interesting thing going on with distance here. Right? We first started off with talking about lengths, then we said that we can use circles and come up with sort of lengths associated with circles. Then we noticed that there was a way to relate distances and times to get this thing we all sort of have a feeling for called speed. And we manipulated that a bit, and we came all the way back around to distance. By taking a special speed, the speed of light, multiplying by a time, we end up with a distance. So we've sort of just been talking about distances all along here. It's an important topic. It's one of the first topics we need to deal with. How far away things are, how close things are, how big things are, how small things are. Okay, so one way of thinking about what we just did here is we were dealing in one dimension, right? Lengths, one line. But that's not the only way to talk about how much space things take up, how big things are and how small things are. I can move to the next dimension. I move to the next dimension. If I talk about lengths being the first dimension, what's the second dimension?
Time.
So you've all heard of the term dimension. There are rigorous and there are less rigorous ways of defining it. But does anyone have an idea or a suggestion by what we mean when we use the idea of dimension? Anyone?
Is that length times width times height?
Well, that may be a calculation we'll do. But what do we mean when we say dimension? Anyone? The idea of dimension is how many units do I need to measure quantity. That's the most general sort of basic idea of what a dimension is. So how many units do I need to measure a length? If I give you a length of 16 meters, how many units did I use? Units, be careful. I'm not saying how big is it, I'm saying how many units are one unit mentioned. Just one, right? I just said meter one time. So it's 16 meters is the measurement, but I only used one unit, and I called that the meter. How many length units did I use when I talked about speed? Let's say a speed of 100 kilometers per hour. How many length units did I use? Just one, right? Kilometer is the only length unit. The other unit there is a unit of time, right? But that's not a length unit. So I'm still only one dimension in length. And I'm also one dimension in time, but we'll just say one dimension in length. But now I want to move to the second dimension. And I'm going to use length and distances as my guide to start off with. When I move to the second dimension, what I'm going to need to do is have two different lengths that I have to involve in order to do that. So the simplest way to think of that is I'll have something that's shaped like this. And what lengths do I need to measure? Well, I'll measure this length. Maybe we'll call that the height. And I'll measure this length. Maybe I'll call that the width. Right? You could call it a lot of different things, but I just decided to call it those two things. Yeah?
Is that three-dimensional?
No, it's not three-dimensional.
It's 2D.
It's only two, because I only need to measure this way, and I can figure out how much space this covers.
Because I'm not used to like the term that you're using for height. It's like, I'm so used to length, that's why.
Sure, you could say this is length, and this is height, if you wanted to. These words are just standing in for what we're really talking about, which is measuring a distance. This is distance number 1, and this is distance number 2. There's two different distances. But if I really wanted to be careful about this, the way I would describe measuring this dimension is that I need two different units. They're the same unit probably if I use the same scale. Right? I would measure this in meters, and I'd measure this in meters, but I need both of those things in order to describe how much I can cover. This concept, how much space in 2 dimensions something takes up, is called an area. Right? You've all heard of this before, and you have all sorts of formulae that you know that are related to area. One relationship you may have is you might have two different lengths. Right? For a square, if you wanted to find a square area, let's say we call this L for length, and this L for length. If I wanted to find the area of this square, what would I do?
Multiply the 2 elsewhere.
I multiply L times L. In the case of the square, they're the same. In a rectangle, they'd be different, but in this case, it would just be L times L. That's one way of writing it, but the other way to write it
Elsewhere.
is L squared. Why do we call that little 2 squared? For exactly this reason.
It's the same as L times L.
L times L is the same thing as L squared, and the reason the word square is used because it conjures up immediately in your head the vision of a square. L in one direction, L in the other direction, multiply them together. How many units of length do I have if I could talk about this area? 2. So if I needed to describe it, the unit would be something like meters squared, or kilometers squared, or centimeters squared. Those are all area units. They're lengths times lengths. And typically we like to use the same one, because then we can just sort of push them together. So if I had a width of, say, 1 meter, and a height of, say, 1 meter, what's the area of this square? The area in this case would be 1 square meter. So you could write out square meter, or you can use the shorthand, m squared, which is really just the shorthand for m times n. The thing to keep in mind when you do this is that these units may be a little bit interesting as you go through. They may throw you off a little bit. One thing we've discussed in this class before is that 100 centimeters is 1 meter. This is a conversion that we have used before, at least in the other lectures, or you will use from time to time. Right? So you might be tempted to say that 100 square centimeters is a square meter. That seems like it might be nice. You might just put a 2 here and a 2 here, but you wouldn't be right. Does anyone know why? They're different units.
So what was the question?
They are different units. So this is correct. 100 centimeters is equal to a meter. But I want to measure areas instead of lengths. So some people are tempted to say that this is true. Right? Just put a 2 above each one, but that's not right. Why is that not right?
Because like you multiply the 200, it's not going to be.
Well, if you think about the rules of algebra, you have to do everything to both sides, don't you?
Yeah.
So really what you need to do is not this, but what?
Square root 100.
I'm going to use the abbreviations. and I'm going to raise both of them, the whole thing. Right? That's the key. You have to raise the whole thing to a power. So now what I see is that, yes, I'm going to get that square centimeter. And yes, I'm going to get that square meter. But what else is going to happen? Well, that 2 is going to hit that 1. What's 1 squared? 1. So that's not a problem. But it's also going to hit this 10 to the 2, this 100. What's 100 squared?
10,000.
10,000. Or, what do you do when you raise something to a power to another power?
Multiply.
Multiply the exponent. So 2 times 2 is?
4.
4. That is the conversion between a square centimeter and a square meter. That throws people all the time. That's hard to kind of get your head around, that there's 10,000 square centimeters in a square meter. You'll also see this effect showing up in other ways of measuring too. Whenever you need to translate between one unit of area and another unit of area, you'll often want to refer to what you know about lengths, because we often think in lengths. But you have to remember that you've multiplied 2 lengths together whenever you're doing this. So we start off with areas, and we get very interested in them. But there's another thing we can think of, not just squares, but there's another very important object that we're going to find a lot. So one of the important objects is the circle. Okay. If I wanted to find the area of a circle, does anyone remember what that is? Pi times the radius, we'll call that r, squared. But in this class, pi is 3, so we can just say that's 3r squared. So if you ever want to know the radius, the area of a circle, and you know the radius, square that radius, but then you have to remember to multiply it by 3. It's a little bit different than the square, right? The square, you multiply 2 sides together. In the circle, you multiply the radius by itself, and then you multiply again by 3. That's one type of shape. Here's another shape. What if I have a globe? Stars are globes, planets are globes. I'm going to imagine these globes. The word for this typically is sphere. I'm going to have a sphere, and I want to know how much paint I need to cover that sphere. I want to know how I can cover the entire sphere with something. I want to know the area, or we usually call it the surface area of a sphere. Does anyone know what the formula for the surface area of a sphere is? The first thing you need to figure out is, what's the radius of a sphere? Well, fortunately, the definition I used before still works. So the radius of the sphere is just to the outside to the center. That's the radius. So let's say I know the radius of my sphere, and I want to know how much paint I need to cover it. The formula for surface area of a sphere is 4 times pi times the radius of the sphere squared. Well, again, in this class, pi is 3. So what is it actually we're going to be using? 12r squared. We'll use that quite a bit. So you'll take that radius and you'll square it, but if you forget to multiply by 12, what you'll find is that you're usually off by one number in that exponent, and that can be a problem, right? So the hope for some people is that, oh, I know the size of Earth. I know the radius of Earth is 6,300 kilometers. So I'll just square that number, and that'll tell me what the surface area of Earth is. Not quite. You can square that number and you can get close, but you're actually 12 times too small. You need to multiply that number again by 12 to get there. Okay. So, are there any questions about areas? One more thing we need to get through, and then we'll be finished. We want to make sure everyone understands how areas work.
You said before we can find the area, we need the radius?
Of a sphere. If you want to find the surface area of a sphere, the easiest way to do it is to figure out what the radius is. Now, there are other ways to do it too, right? If I could get a big bucket of paint and paint the whole thing, I could count how much paint I used, and that would tell me. But often in this class, what we will figure out is we'll know what the radius is, and then from that we can calculate the surface area. But that's one way of doing it, and this is a very powerful method. We'll use that a lot. The same thing with the circle. Right? Another way of figuring out how much space a circle takes up is by taking 3 and multiplying it by the radius squared. All right, everyone okay with this last part?
Yeah.
Okay. Well, we started in 1 dimension, we went to 2. What dimension do we actually live in? 3, so we better talk about 3 dimensions. What's the thing that measures in 3 dimensions? It's the same idea as moving to a square, but now I'm going to move to the 3rd dimensional analog of a square, which is what? A cube. So it's kind of fun to think about how we constructed the square. The way we constructed a square is we put 2 lines and we connected them, right? So 2 one-dimensional objects connected gave me a square. The way to make a cube is to take 2 squares and connect them. That's a cube. And you may have heard all sorts of ways of describing how to measure the different lengths along the sides of a cube. For example, this might be the length. This might be the width. And this might be the height. Right? Those might be ways that you've heard of describing these things. Maybe we call each side, just since it's a cube, they're all the same length. This one is going to be an L. This one's going to be an L. This one's going to be an L. Right? What can I measure 3-dimensionally? If I wanted to figure out how much space a 3-dimensional object takes up, that concept is called volume. And I will often want to know the volume of things. In fact, in the homework, you're asked to find the volume of a cube that's the size of the universe. Well, how do I do that? I have 3 different lengths. And I want to multiply them together. So it's just going to be L times L times L, isn't it? What's another way of writing that? L to the 3rd. Or another way of calling 3rd is what? Cubed. That's why. Right? The connection between a cube and that 3 comes right there. Let's say each one of these was 1 meter. What volume of a cube would I get then?
1 cubic meter.
1 cubic meter. I could write it like this. 1 cubic meter. If you go back, there's a discussion in one of the lectures of how to calculate the conversion between a cubic centimeter and a cubic meter. Right? I recall before that 100 centimeters is equal to 1 meter. If I wanted to figure out how many cubic centimeters are in a cubic meter, what can I do? Well, I can cube both sides. Right? That cube hits everything. It hits the centimeter, and it also hits this number here. So that's going to be 10 squared to the 3rd power. What's 10 squared to the 3rd power?
10 to the 6.
10 to the 6. What's another word for 10 to the 6? In English, what would we say 10 to the 6 is?
Not a million.
Million. 1 million centimeters is a cubic centimeters is a cubic meter. 1 million cubic centimeters is a cubic meter. That's pretty amazing. Think about a cubic centimeter, right? Centimeter by centimeter by centimeter. How many of those cubes do you need to fit up a meter by a meter by a meter? Why, it's 1 million. That's a way of thinking about what 1 million is. It's kind of a neat way of thinking about it. We have an idea of a centimeter. We have an idea of a meter. In the 3rd dimension, things get rapidly out of control. Raising something to the 3rd power is a powerful thing to do. Yeah?
Wait, so you did the second one, like, yeah, up.
Mm-hmm.
So how you did the 3?
The 3. Whenever you raise something to a power, and everything is in the parentheses, and everything in the parentheses is multiplied, which this is the case, because it's really 100 times a centimeter, isn't it?
Oh, okay, I get it. So
That means that everything needs to be raised.
you made the 100 to
I made 100 into 10 to the 2. Yes, that's right. So this is one way of thinking about a volume, but what are some other things that we might want to take a volume of? Well, in this class, of course, we're dealing with spheres and balls and globes, so let's think about what those look like. Here's my sphere again. We already have the idea of what a radius is. Does anyone know how to calculate the volume of a sphere if I know the radius? That's okay if you don't. This is the answer. The volume of a sphere, I often use capital V for volume, is 4/3, not 4, but 4/3 pi r to what power? Cubed. It's always going to be cubed because remember what we said? You have to have 3 units there. In order to get the 3 units there, pi doesn't have any units. The only thing that's a measurement that has units is r, so we have to multiply by itself 3 times. But in this class, pi is equal to 3. So what is the volume of a sphere in this class, approximately? 4r cubed. So you take the radius and you multiply it by itself 3 times, and then you have to multiply by 4. But once you do that, you'll get how much space something takes up, like the Earth, let's say. So now I have this concept of volume, how much space something takes up. I can come up with something that's sort of similar to speed, but involves 2 different things. It's still a ratio. The way speed was a ratio was a distance divided by time. This is going to be a ratio, but it's a slightly different one. And the ratio is going to be the amount of stuff that I have in the object divided by its volume. That's going to be a different concept that I'm going to come up with. But a lot of the same mathematical machinery that you use to talk about speeds can be used to talk